So let me go back. So let us say if we can create a set, if we can create a set phi and t where over a comma b for every n comma m integration a to b phi n t phi m star t dt is equal to 0 holds for n not equal to m, and for all n a to b phi n t mod square dt is 1. We call this set as a set of orthonormal functions. So phi n t is called set of orthonormal now. If every function, now this function I am writing a star, assuming that this function is square integrable, well defined in a to b, if every function over a to b can be represented as a linear combination of functions. Right now we can call all in phi n t. We call this set phi n t as complete. Why complete? Because this set phi n t can represent every possible function over a and b, with a star means that function must satisfy some properties. And if at all this holds, that this phi n t, if any function over a and b with this star can be represented as a linear combination of functions over phi n t, then this set phi n t is called as. So we are not digging deeper into this. Otherwise, if you want to read more about it, then you can go to the text maybe, or you can go to the course of functional analysis. I am just telling functional analysis, and over that you can study the space of L2 functions. Okay, so there you will find a lot of details about it. But right now in our course, we only need to know the meaning of what comes. Okay, nothing more than that, because this is out of our usage. We don't need to use much from it. Okay, so this is called as complete. So I think we are not proving it, but the same functions which we have used, same functions in the cardinal series is a complete set. Okay, so because I wanted to use this definition or use this property, so I had to introduce the concept of complete set. Okay? So it's a complete set, means that every function over minus infinity to infinity can be written as a linear combination of shifted sinks or sink functions. They are orthogonal. We have already proved it. So now we are formally stating it, that let Wt be a practical waveform. It means finite energy, practical waveform, and it is defined for all values of t that we wish to represent, over interval a to b. Suppose we consider an open interval by the series then Wt can be written as summation a of n by n t. Okay, where a of n is given by 1 upon kn integration a to b Wt by n star t dt. Okay, where what is k of n? K of n is nothing but the norm of phi n t. Okay, so I am writing it down, although I have introduced it, but let me write it down. So right now we have not yet said that whether this set is orthonormal, but at least we know that it is orthogonal. Okay. Here the condition was that phi and t, set phi and t must be a complete orthogonal set. So I have just formally stated what I have just discussed about. Okay. This is a formal statement saying that if let us say Wt a practical waveform means it has a finite energy, it is defined for all values of t, it has finite number of discontinuities if at all it has. So then means you can just try to see the conditions if you are required to have a Fourier transform. 90% those 99% those conditions will apply here for any practical waveform, or maybe some tighter versions of those conditions which we studied in the course signals and systems for some Fourier transform to exist. Okay. So let Wt be a practical waveform that we used to represent over interval a to b by the series. Then we can write Wt as this, as a series, this where the coefficients of the functions can be obtained by this. Okay. And phi and t, but for this to be valid, this phi and t must be a complete orthogonal set over a. There may be some sort of disagreement over taking a closed interval or an open interval, but let us, in order to avoid any sort of problem, let us take an open interval. Okay. So with this as the background, I think we stopped at this point, yeah, where we proved that this is orthogonal. So we were basically proving this theorem. So let us move ahead now, okay, and prove this completely. We had to take a detour in order to know this. So coming back to the proof of the theorem, coming back to the proof of the theorem. So a of n can be written as f of s integration minus infinity to infinity Wt pi n star t d of t. Okay. Now, from where does this come? Let me just take you to the theorem. So this was the theorem. Okay. So we said that Wt can be written as a linear combination of the shifted sinc functions, or this is sine of argument upon the argument. This is sinc function. So it can be written as the sum of shifted sinc functions. So initially we have shown that these shifted sincs are orthogonal. That we showed that day. Okay, this was the proof. Now it remains to show that a of n is this. Now this is simple. This can be easily seen from this statement which we have written, that a of n is nothing but the integration a to b Wt phi n star t. So that is what we have done here. But now how do the sampling comes here? That if at all your f of s is greater than b hertz, then this Wt is W of n by fs. So we need to prove this only. So that is what we are now moving. So using the Parseval's relation, Parseval's relation or theorem, whatever you call, we can say that this is equal to f of s integration minus infinity to infinity W of f with phi and star f d of. Okay, that is this. You can call this to be an inner product. This inner product of two functions over time is same as the inner product over the frequency. So you can use either of this and you will end up at the same result. Now substitute this. Substitute this. We have obtained this. I think, let me show it to you that we obtained this. I think I have written, yeah, here it is. So the Fourier transform of sinc function is nothing but 1 upon fs. This is the direct function which holds from minus fs by 2 to fs by 2 with the value of 1. So we substitute this, so we get that a of n is equal to minus of fs by 2 to fs by 2 W of f into e raised to power j 2 pi f n by f of s d. Okay. Now remember that there is a star here. Okay, this star. So what happens that if we go from this, so this Fourier transform shifted sync was this expression. So this minus of j will become plus of j. So please do not make such mistakes in the exam or wherever you are doing this derivation, that try to take care of this star function or this conjugate thing which you need to do. So once you do it, now here comes the sampling or the band limited view of WT into rho. So if WT is absolutely, so this word means that it has no component outside B, absolutely band limited to B hertz with, and the sampling rate, or if we have chosen Fs to be greater than equal to 2B, what is the meaning of this? Let me write it down. The Wf is equal to 0 for mod f greater than B. Okay, where B is less than Fs. So I am just, whatever I have written, I am just writing it in short. So this is what we mean. If this is the case, it means that if you have chosen this as the case, that if Wf is 0 for mod f greater than a b, it means that Wf lies only from minus b to b, and this is the relation for b and fs. Then limits on the integral, in, let us say, 4 may be extended to minus infinity to, okay, without changing the value of the integral. So now this becomes that a of n is nothing but integration minus infinity to infinity w of f e to power j 2 pi f n by fs d. Okay. Now this is nothing but this is inverse Fourier transform of w of f evaluated at t equal to n by f of s. So consequently, a of n is simply w of n by f. Okay. So this is the proof of that. Means you can derive the sampling theorem through this cardinal series as well. And this was the underlying principle of Claude-Shannon's derivation. This is generally not given as the initial development of sampling theorem. Whatever we have done at the start of our lectures, it means we took an impulse train and we multiplied it, and then we said that in the Fourier transform this is a convolution. So that is a more what do you call an not intuitive, but what is you will feel. Let us say if you are told that you need to sample something, so you will immediately feel that let us multiply it with impulse train. Okay, so this you will feel. So once you feel this, then you will derive it. But what Shannon started with was this Whittaker's series, cardinal series, okay, and he came up with this. So both ways you will get the same result. So the minimum sampling rate, I am not right now not commenting on this, that why do you get this. So this should be left as some sort of a thinking homework, that why this condition is required. If at all, if it is less than, then what will be the problem? Okay. Okay, so such things are left for you to think, and maybe they will form part of the exam. So the minimum sampling rate, but be assured, whatever we have discussed in the lectures, you can derive anything. Let us say whatever questions I am asking or relegating to homework, you can easily derive those things. Okay, so the minimum sampling rate allowed to reconstruct a band limited waveform without error is given by Fs minimum to B. This is called Nyquist frequency. This we have already defined, but I am just, for the sake of completing this theorem, I am writing it. It is called as Nyquist frequency. Okay. So I think we are done with this. So now let us start. So there are two important things which I need to discuss with regard to the sampling, which is generally asked at a lot of places. Okay. So two important things. First one is the band pass signal instead of band limited or baseband. Band pass signal. What will you do? So right now, up to now, what we have discussed is, let us say this was a zero frequency. We said that there is some signal which is limited to minus W to W. But what about, let us say, if I shift this zero frequency to some frequency? It means that let us say this is some f of maybe carrier frequency, and this is some f of C plus W, and this is f of C minus W. But the span, it means that this is still W, and this is, let us say, you can take it to be 2W, and this is also. But generally, we will say that the bandwidth is W. So we will sample and get one. So how will you determine the sampling rate of this? Okay. So this is one very, very popular question which is generally asked, maybe in interviews or in laboratories or wherever possible. Okay. So we'll answer this question. We won't be taking the analytical step to answer this, but we will tell a way that still, even if there is a band pass signal which is centered around some carrier frequency, this carrier frequency can be anything. It means it can be 5 Hertz, 10 Hertz, megahertz, whatever practical frequencies which we are using right now, you can relate it to that. And around that frequency, if you have your signal. So let me write it down. So a band pass signal, so BP for band pass, so a band pass signal whose spectrum exists over a frequency band FC minus, I should use W. So to be consistent, let me just use the notation which we need to write. So this should be W2, should be minus W2, so the next band should be W. Unnecessarily confuse you. This is okay. This is W2. This is so a band pass signal whose spectrum exists over a frequency band FC minus W by 2. Now, what is the meaning of this? See, there is one very important thing to mention here, that An analogous spectrum exists at minus f as well. Okay, it means minus of fc. There will be another copy. Okay. So you can just correspondingly write down the limits. Okay. This should be minus of fc. Again, I think plus w by 2. This should be minus of fc minus w by 2. Okay. So you can write this is another. That's why this mod comes. Okay. Is a bandwidth W hertz. Such a signal is also uniquely determined by samples taken at above the Nyquist frequency to W. Okay, so we said that if at all the bandwidth is W, then still you only need the rate to be slightly higher than 2W to recover the signal. It is so the theorem doesn't apply only to baseband signals. Okay, here minus W by 2 W by 2 in total positive and negative frequency the bandwidth was W. Okay, but generally we say that band limited to W by 2 volts. Okay, so the sampling comes out to be rate comes out to be W. But here, if at all, this total bandwidth in the positive side is W, so you need to sample at a rate 2W. This is an established fact. Okay, so you should not confuse between passband and baseband signals. Now, for this, so one idea is very basic idea that bring the signal in the band pass signal to baseband and sample the in phase. We have yet not introduced these terms. I think in subsequent lectures we will introduce them. Quadrature phase, at least I think you know about these from your introduction to communication systems course, at least somewhat in quadrature components. And regenerate and then regenerate the band pass signal. Means if at all we need to explain this, if at all we need to say that yes, this is feasible, that if at all the bandwidth is W of this passband signal, then I need to only sample at 2W. So one of the ways is, which seems to be inefficient, that we bring this band pass signal to the baseband. It means we convert this signal to a signal of this form. Okay, but now this signal will have two components. Okay, one is the in phase component and one is the quadrature phase component. And then you need to sample the two components and then regenerate the band pass signal. Okay, so this is important. Now, even directly we can derive. Derive the above fact. For this, refer to. This is not required, but for the interested reader, I am giving the reference of the paper which discusses this quite well. A discussion of sampling theorems. This I will upload it in the class drive as well for those who are interested to read it. This is a paper which is written by D. Ellington, okay, published in IRE 1959. Quite an old paper, but well written paper. For those who are interested, they can go and read it. But for us, for most of us in the course, this suffices that if at all there is a passband signal which has a bandwidth of W, we only need to sample it at a rate which is greater than twice of W. Okay, so Nyquist rate for this signal will come out to be twice of W. For this is W. Okay. This is the baseband signal. This is just a somewhat a way we can think. This whatever written is a way to think. Even the development for this is given in this paper. So if you need to be very specific that really how does it come, why it is still 2W, why not W only, because once we have shifted this whole thing to baseband, it should come out to be W only for the in-phase and quadrature. So for such questions, you can go back and read this paper. And if at all, those of you who go back and read, they have any doubts, we can discuss it in a separate session. Okay? Right now, this is not the focus of the course. Now, second important thing. Okay? Possibility of, this is generally asked at a lot of places, possibility of Fs is equal to V. It means sampling exactly at night. Sampling exactly at Nyquist rate. So we have not yet said anything about it, so it is important to discuss. Okay. So let us start with an example. So suppose you are given a function, a sinusoid 2 pi b t minus t. Okay. This is band limited to b hertz. Okay. Now, as per the Nyquist criteria, start taking samples from t equal to t naught at 2b samples per second. Okay. So what you will get? You will get all zeros. Okay, this is an established fact. You will get all zeros. So what is the problem? We have sampled this signal at the Nyquist rate, which is 2b, but still we are getting all zeros. And we cannot recover, sine 2 pi b t minus t naught from this sequence of zeros. So what is the problem? So the problem is that for sinusoids, the sampling rate should be strictly greater than 2b. Now the reason for this is, let us see the spectrum of sine. The problem is that sine function has impulses. Okay? One impulse will come at p, another will come at minus p. Now if we, let us say if we consider the derivation which we did for the sampling theorem, we said that if this is the spectrum of the signal which is to be sampled, this will repeat. It means this will shift to f of s. Suppose this is my 2b. Now if this is my 0, so this impulse will come at this point. It will overlap this. Okay? And there will be another impulse at this place. So this overlap is the reason. So we need to write that. So if GF contains, if G of F, spectrum of signal to be sampled, spectrum of signal to be sampled, the name is G of T. If G of F contains an impulse, at the highest frequency, so if it contains an impulse at the highest frequency, then the equality then the equality must be removed, or else overlap will occur. Now this equality means the equality in f is greater than equal to 2. So now, because the spectrum of the signal to be sampled sine function contains an impulse at the highest frequency, because the highest frequency present is B. So if it contains an impulse, so we need to now remove this equality and the sampling rate has to be strictly greater than B. Okay. But for other cases in which there is no impulse at the highest frequency, this equality will work. It means theoretically fs equal to 2b should also give you back the original signal if you try to reconstruct it through the sinc functions. So pretty much these were the two very, very important things which we wanted to know, at least after studying the sampling theorem. For this you can go and read page 253 of BP Lati and Dink's book. I think Dink's. This I will mention it in the lecture breakup file as well. So any doubts, any questions, or any comments at this point? You can very well say.
Hello, sir.
Yeah.
Sir, in the Shannon-Whittaker theorem that we were talking about, you wrote a statement that WF equal to 0 when Fs is less than mod B. Is that a condition for the sampling theorem?
Can you just repeat me what did I write?
Sir, you wrote a statement and boxed it. WF equal to 0 and F should be between the range mod B less than mod B. So is that a condition for the sampling theorem of Shannon-Whittaker?
See, yeah, we basically are studying the sampling theorem for band limiters. So what is the way you specify a band limiters? Yeah, I now understood yourself. So I must have written WF is equal to 0 for mod F greater than B. I think this is the statement. Is it right? You are referring to?
Yes, sir. Yes, sir.
Yeah. So this is the basically this is band limited signal. So we.
Okay, sir. Actually, sir, I misread it. I read mod F is less than B.
So then it's a different signal. Mod
Yeah.
F has to be, maybe if I have written at some place less than B, then it is not correct. It has to be greater than B. Because we are, what does this mean? Or we can say that WF is non-zero, only in mod F less than B. Then it's right.
Yes, sir. Yes, sir. Maybe I read wrong.
Yeah, okay. So basically meaning यही है कहने का कि इस तरीके का सिग्नल होना चाहिए 0 के अराउंड for some, let us say B and minus B. For all these things it should be 0. Right now we will be studying that even this sort of signal cannot exist. Okay. Now we will study this. So last point of sampling is reconstruction or anti-aliasing filter. The concept of anti-aliasing filter we will now study. Yes. So any other issue with anyone? Any doubts? See, I would say that okay, if some of you miss some lectures, so there is no problem with that. Because for this course particularly, I am deliberately giving references for each lecture. I am saying that even this section you should read, this section from this textbook you should read. So go back and read it, and then if you have any doubt in that, then you will have a discussion in a separate session. That separate session can be arranged through emails. Okay, you can write me an email that okay, this I couldn't understand, or we as a group of 5-7 students couldn't understand, and we would like to talk on it separately. Then you would definitely do that. Okay. So to make things work smoothly for both the parties, it means for me and you, I am giving you the references for each lecture as soon as the lecture gets over. So you are not lost. Secondly, I am giving you the problems as well. So once you just read the lecture from the text which I have given, you can just solve the problems and you are then prepared for the exam. So these problems will form the base for midsem and endsem both. So it will have an overlap. Means most of the problems will be around the problems I have given in the lecture breakup file and whatever we are covering in the lecture. So for that, these PDFs I will upload. I generally upload after every lecture. We'll continue doing that. So you can just go through these handwritten PDFs. Now, so let us now go ahead.
Sir,
Yeah,
can you please upload the PDFs of the textbooks as well?
PDFs of the textbook. See, this can be done, but this is legally not allowed. We should not download and upload it in class twice at least. What I can do is that, if at all possible, I can send this PDF to one of you and then you can circulate it among the group. Will it be possible?
Yeah, that would do.
Okay.
Yes,
So,
sir.
so I should send it to which email ID? You tell me one email ID. The person who is most reliable and he will send it to all. Tell me the email ID. Or the person who has just asked, you can circulate.
Yes, sir, sure.
Yeah.
Do I mail you my email ID or write it in the chat box right now?
Or you just email me, okay? Then I will reply over your with the.
Okay, sir.
I will try sending all the soft copies to you, and then you can circulate it among them. At least because legally this is not allowed, we should not do it in our class. Okay, from the institute's policy or copyright policy, downloading soft copies and using without paying is illegal. So we can do it at a personal level. So you just send me an email after the lecture, and I will arrange the books. Okay. Now let us. So with this, I think for band pass done and for sinusoidal signals. So ये बहुत important question है sinusoid signals का. आप remember रखिए कि f मतलब याद रखिए कि fs जो है वो 2b से बड़ा होना चाहिए. Strictly different. क्यों? क्योंकि impulse है. Impulse की वजह से क्या होगा अगर हम वही logic लगाएं सैम्पलिंग थ्योरम का कि shifting of the spectrums, तो ये overlap जाएगा. So at the highest frequency there should not be any impulse. So because in sine and cosine you have an impulse, so you cannot sample them at exactly at the Nyquist rate and recover. You need to be strictly at the Nyquist rate. So one more thing I need to say about the signal reconstruction. I think we have seen the reconstruction formula that. Just write it down. So few remaining things from signal reconstruction. Okay. So we directly derived, I think, let me then show, or I think if you remember, I think you must be remembering that we derived, or let me write it. So what did we do? Yeah, we found out that g of t is simply summation n is equal to minus infinity to minus infinity g of n by 2w sinc of 2w t minus n. We derived it through some analytical expressions. So this you can just refer to lecture 2. I think the PDF file contains this, as well as the reference which I have given contains this for t less than infinity. But we never said that how really you are going to generate GT. Okay? How this will be achieved, how this series can be generated. So now we will be discussing a few things about that. So let me write it down. Oh, one more expression I need to do again. Here. Okay. And we said that if at all the rate f of s, the sampling rate, is greater than or equal to 2b, the Nyquist rate, then g of delta f, the spectrum of the sampled signal, it can be easily written as f of s, g of f plus f of s summation m is equal to minus infinity to infinity, m not equal to 0, g of f minus m naught. What is the meaning of this? It means that there were shifted spectrums. After you do the sampling, So this is the sort of signal you will get. So this repeats. This is f of s. This is twice of f of s. This is minus of f of s. So if at all you are given a sampled signal, okay, this is the spectrum. This is f and g of delta. So the ideal strategy to recover the signal, the original g of t, is apply a low pass filter. Okay? You just take this spectrum out. So in the frequency domain, if at all I can do such a filtering, then theoretically I should get GT back. So after filtering, after low pass filtering of the sampled signal, I should get back G of. So that is the concept which we are going to now write it down. So the principle following this is, because of a term, what is the term here? Term is f of s, g of f. Right now, because our sampling rate was greater than 2b, this is not corrupted. So this is important. If at all your fs is less than 2b, then this becomes corrupted. Why? Because the shifted copy comes like this. So to ensure that this is not corrupted, we have to choose f of s has to be greater than equal to 2b. So because of a term f of s, g of f in the spectrum of the sample signal, we can recover GT by sending it through. By sending it means the sampled signal. By sending it through an ideal low pass filter, okay, of bandwidth p hertz and gain 1 by s. So this is important. I think either we consider W as the bandwidth or we consider P. If at all we consider W, then it should be W hertz. This is what is happening if we are changing textbooks. No, we need to, because what I have found out is that any textbook is not completely telling us the things, and we get generally stuck when in interviews or in other places we are asked about these things. So that's why I need to take things from different textbooks and tell it to you, so that our course is complete in some manner, at least from the perspective of sampling. It should be so W. So it should be. So we have taken uses W. So this seems to be quite practical. Once seeing this, that you need to, because this spectrum gets scaled by f of s, so you need to remove this factor and you need to just bring out this band for usage. Okay, so that is can be done by a low pass filter. So let us say, if I say that in the frequency domain, the response of this low pass filter should be like this. That is, it is W and this is minus W, and the gain is 1 by Fs, which is equal to T of S. This is the frequency axis and this is the low pass filter response. You can write mod also to say that it is the absolute value. So what is H of F? The H of F is nothing but T of S, rect function, F by. This I have already introduced, that let us say if this is a rect function with F by F of S or any other parameter, then this lies from parameter minus parameter by 2 to parameter by 2 with a value of 1. So this now the value will become T of S. Now the corresponding time domain value is nothing but 2WTS sync of 2W. Now due to Nyquist sampling rate, suppose we are sampling at the Nyquist rate exactly, not greater than that. So 2WTS is nothing but 1. Why? Because we have chosen f of s as 2W, T of s is equal to 1 by f of s, so this becomes equal to 1 by 2. So because of this 2WTS is 1. So your h of t becomes sync of 2B. So now you can clearly see, if at all I am passing the sampled signal, suppose the sampled signal is nothing but G of, so output would be what? So the sampled signal goes to the filter H of T. The output is convolution of both, and the desired response is original signal, original unsampled signal is the output. So now you will realize, if you do this convolution, you will land up exactly at this result. Okay, this result, which we derived through some different mechanism. So in order to get back G of t from the samples, you need to pass this sequence or this samples through a low pass filter whose impulse response is sync of 2bt. So one observation regarding h of t. So observe that h of t is equal to 0 at all Nyquist sampling instants. Okay, that is t is equal to plus minus n by theta, except at t is equal to 0. This is very, very important. So I will write a hash here, that this will form the basis of every possible understanding you need to develop about the sampling theorem. Okay. So what happens now? Really, what is happening in operation A? So this is operation A. So what happens in A? Let me just write it down for completion. What happens in A? So if you have any doubt in between, you can unmute and say, we will discuss. Okay. So each sample in sampled GT being an impulse generates a sync pulse. Now, why it generates a sync pulse? See, h of t is nothing but the impulse response. It means if you apply an impulse signal at the input, the output should be h of t. So, in sample signal, you know that we have impulses. Why? Because we multiply an impulse train with the unsampled signal. So, once an impulse comes, so output should also be h of t, because the filter itself has an impulse response of h of t. So, it generates a sync pulse of height equal to strength of the sample. Okay, then addition of, because convolution is being done. So convolution says then into shift, multiply, add. So addition of the sync pulses generated by all the samples results in GT. Okay. So this is what was pending. I think we didn't do this when we did the signal reconstruction formula. Generally, when the sampling theorem is taught, so this is the approach adopted, that once you have the shifted spectra, then it is told that just low pass filter and adjust the gain. That is what we have done. TS is the gain, low pass filter it, and the corresponding expression for that low pass filter in the time domain is the sinc function. So nothing but just convolve the sinc function with the sampled signal. Now since sampled signal contains impulses, so as soon as one impulse comes, this h of t, the output will be h of t. So it is basically multiplying the value or the energy in the sampled signal, or sorry, the strength of the sample with the sinc pulse, shift it and add all of them. So for this, I think we can draw a small figure to understand it much better. So I think we have drawn already h of t, h of f. So h of t is drawn below. Let me write it down. H of t is drawn on next page. So you will get that this is your h of t. And this goes on. Okay. So the height is 1. This is your h of t versus t. Okay, and these points are 1 by 2p. Then is 1 by b. Then is, it means that it is multiple. These are multiples of the sampling rate. Now, if this is now being convolved with the impulse train or with the sample signal, so let us see what happens. Suppose if this is your signal you are going to construct. So this was the signal we had sampled. I have drawn the envelope so that we know that which signal we sampled. So suppose the first sinc function comes. So this sinc function will have a 0 crossing at these points. Then there is a second impulse function. This function will also have 0 crossings at all those points where sample takes place. Then again construct this sinc function. So that is the way we do it. So every sinc has a 0 crossing at the other sampling instance. It is only one for that particular sample. It means this sinc function will not disturb or will not have any value being taken with the help of other impulses, because it is always having its 0 crossings at the point where the other impulse comes. So for this, you can just see page 254 of Larky's text, TB, that is textbook. And the homework for this is there is a small homework or a self-reading assignment, you can say, that you can just solve example 6.1. Solve example 6.1 from Larky's textbook. Very good example. So now we are done with signal reconstruction this way. So now the concept of the design of anti-aliasing filter comes. Okay, pre-filtering. So before we start pre-filtering, if you have any doubts or you need to say something, then you can unmute and say. I would be happy to answer. See, if you need to enjoy the classes, then you need to come prepared. It means it's better if you go back and read at least something from the textbook or from the PDFs which I am uploading in the class drive folder. So that way you will enjoy the class. See, I could avoid a lot of analysis while doing the lectures as well, but then that work is relegated to you. It means while you are reading the textbook, you need to understand it yourself, and there comes the problem. It's easy to state sampling theorem by simply saying that it is a shifted spectrums, low pass filter, you will get the signal back. But sorry, but if I don't discuss the underlying mathematics, and once you go back and read from the textbook, you are on your own. So, at the cost of lectures being boring, we understand this. Means बाद में दिक्कत ना आए तो अभी कर लीजिए जो बेहतर है. मतलब whatever I am doing in the lectures, they will help you. It will help you understand the things. I think in a few seconds once you will go back and read. Because while solving problems, you need all these concepts. While telling to somebody that you know this, you need to understand the underlying maths. You cannot save yourself from this analysis, at least in this course. All those courses which have their root in mathematics, you cannot save yourself from the analysis there. So now we come to the concept of pre-filtering. This is also very important concept, and I will say that this is the last concept which we need to discuss in sampling. Okay. So this is pre-filtering or some practical issues in signal sampling and reconstruction. Or some practical issues in signal sampling and reconstruction. For that, one very good thing to discuss is can a signal, so question, can a signal be both time limited and band limited? Is it possible? मीन्स ऐसा कोई सिग्नल जो कि टाइम में भी लिमिटेड हो और बैंड में भी लिमिटेड हो? आंसर तो नो, आंसर इज नो, बट वी विल सी हाउ. Then another question. Can a signal exist for all time? For all time physically? Or in, say, reality? Physical signal. Physical signal means a signal which is there in reality. So can a physical signal exist for all time? The answer is still no. No, it is not possible. See, if you are talking over a cell phone, then you are talking for some time only. You cannot just talk for, let us say, years and years, because theoretically whatever we are doing, the signal exists from minus infinity to plus infinity. So the answer is strictly no. Question. If answer to both the above questions is no, how do we use sampling theorem in reality? Means in systems. How do we use it? Now, why the question arises is, suppose if we say that a signal cannot exist for all time, okay, then it is a time limited signal. So physically, signal will be time limited. Okay. Now the question one tells that if it is time limited, that cannot be band limited. Hence, it is not band limited. If this is the case, then the sampling theorem relies on band limited nature of the signal. But since sampling theorem relies on band limited nature, it cannot be directly applied. So whatever we have studied has now given us a problem basically. Okay, that we got to know that if at all there is a signal which exists from minus infinity to plus infinity and it is band limited, then so we can recover it from its samples. But there is no such signal in reality. So how do we do that? Now how do we apply the sampling theorem to a real time signal? Okay, real time means that whatever signals which we are now using in systems. Now there is a proper proof for it, that can a signal be both band limited or time limited. Okay, so let us see it. So for this, let me just tell you a small thing, because ये बहुत एक concept है जो कह दिया जाता है, but इसके बारे में ज़्यादा बोला नहीं जाता है. तो first let us see a small thing about this. This is question 1, question 2, and this is question 3. So question 1. So answer/justification. Question 2, question. So what is it? Now suppose that suppose that is a signal, suppose there is a signal, suppose a signal is simultaneously band limited in time. Okay, suppose there is a signal which exists, so that g of f is equal to 0 for mod f greater than b. Okay. So if this is the case, then I can write g of f as, if this is the case, g of f multiplied by a rect function which has a greater frequency, what means that b prime is greater than b. How? जैसे कि suppose g of f जो था आपका एक इस तरीके का स्पेक्ट्रम था. Okay, it was band limited to minus b to p. So I can say that this is nothing but this is equal to the same signal but multiplied by a bigger rect function. Okay, here this is b prime by 2, here is minus b prime. This is b, and this is minus b. Okay, 2b, so it has to be b prime. Okay, so if at all I can write, that is correct. This is correct because this holds from this property. Now, so this implies that g of t is equal to, let us say, if at all this is the case, then g of t can be written as g of t's convolution with sinc function. Okay, sinc is 2b prime t. Now, can this signal be time limited? Can this be time limited? So this is the question. Answer is no. But why? So let us discuss. So those who are there and listening in the class, can they tell something about it? That can this convolution give you a time limited signal? It means g of t is being convolved with the sinc function. Remember that this sinc function exists from minus infinity to plus infinity. Now, if at all you were asked to derive this convolution, what you generally do is that you shift one of the functions around the 0. It means you just flip it and then you evaluate this sum over all possible shifts of this function. So with this as a background, can you tell that why this cannot be time limited? Anyone? If you need to say any of your theory, you are most welcome. It means that
But
we
like
can, yeah.
sync function can be shifted to like an infinite number of positions
Okay.
to get different outputs, right?
Yes.
So that will lead to a g of t being like a continuous infinite function.
Yeah, that is one aspect. You are absolutely right that I can, suppose this was the sync function. Suppose this was the sync function and this goes. Now the problem with this sync function is not time limited. This stretches from minus infinity to plus infinity. Now if I flip this sync function and I shift it to the most possible left limit, it means I take it to minus infinity. Flip sync and then टेक इट टू माइनस इंफिनिटी, इट मीन शिफ्ट करो उसको माइनस। तब भी क्या होगा, जो सिंक आपका माइनस इंफिनिटी पे शिफ्ट हुआ है उसका कोई ना कोई कंपोनेंट चाहे बहुत छोटे लेवल का होगा वो इस सिग्नल से मल्टीप्लाई हो जाएगा। तो इसका मतलब ये कि जो ये नेट रिजल्ट है ये विल ऑलवेज लाई फ्रॉम माइनस इंफिनिटी टू प्लस इंफिनिटी। इसको कहते हैं दैट्स बिकॉज सिंक फंक्शन हैज इनफाइनाइट सपोर्ट, बिकॉज सिंक फंक्शन has infinite support. Infinite means that it exists for all time. Infinite time के exist करता है। Infinite support for this convolution, the above convolution cannot give time limited output. Okay. So this is a very loose proof of this fact. Why I am calling it a loose proof? Because this proof works for us engineers, that we don't need to go into difficult mathematics to understand this, that if at all something is band limited then it cannot be time limited, and there is a vice versa proof also given in the same manner, that if at all the signal is time limited then it cannot be band limited. So ये इसका आंसर जो नो है वो ये कहता है कि साइमल्टेनियस नहीं हो सकती, मतलब साइमल्टेनियसली one thing can be time limited and band limited as well. But yes, there is one possibility, there is signal can be time unlimited and band limited unlimited, ऐसा भी हो सकता है। ठीक है, ऐसा नहीं है कि टाइम अनलिमिटेड सिग्नल को बैंड लिमिटेड होना जरूरी है। मतलब आई थिंक इफ यू कैन recall, मतलब if you can understand it well, so only one thing we are saying, that it cannot be a signal cannot be TL and PL ports, but it can be time unlimited and band unlimited ports. ये हो सकता है, ये नहीं हो सकता। So इसका जो प्रूफ है वो इस बेसिकली लूजली इस तरीके से दिया जा सकता है। तो ये कहता है, इसकी वजह से क्या हो गया है कि अब आप सैम्पलिंग थ्योरम बिना प्री फिल्टरिंग करें या बिना कुछ, मतलब व्हाट यू कॉल, आप विदाउट डूइंग एनी गुड अरेंजमेंट यू कैनॉट अप्लाई द सैम्पलिंग प्रैक्टिकल सेटिंग्स। Yes, somebody wants to say something? Modi Kunj Kumar, yes. You want to say something? I think he is unknowingly on mute. Okay, ignore him. So I think we can, for today's class, we can stop at this point, because in the next class we will start with pre-filtering and then we will go to PAM signals and then PCM. So this is the last part of module 1. We will most probably try to complete it in 7 to 8 lectures, and then we will shift to module 2. Okay. So for today's class, I think this suffices. So if you have any doubt or any comment, then you can stay back. I am there.